Okay, the next thing that we're up to is displaying the sample data and describing the samples. So to do that, the first thing we need to do is we need to make sure we have the right sort of graph. And what we need for this is it needs to be a dot plot. The reason we need a dot plot is it's the best way of just showing the distribution. We can see everything that's happening. We can get all the summary stats we like. We can find out about the mean and the median and the upper quartile and the lower quartile and the minimum and the maximum and if we really get into a little bit more detail, we can look at the kurtosis and the skew and all sorts of things. And none of it actually tells us, as well as looking at the picture, what's actually happening. So we have to have the picture of the data to look at. And once we look at it, there are 4 things in particular that we want to talk about. The first one we want to talk about is the center or the shift. Right, so we're talking about where the center is the highest and whether or not the boxes or the middle 50% have been shifted at all. The next thing that we want to look at, after we've done the center and shift, the next thing that we want to look at is the shape. Or another thing we want to look at is the shape. Here the key thing we're looking at is it normally distributed or is it some other sort of distribution? We also want to know which one's more spread out. Are they equally reliable, or is one of them more spread out than the other? Basically, the more spread out something is, the less reliable it is to talk about it, which means that the wider our confidence interval is going to be. Right? And the final thing that we want to look at is any unusual features. These can be individual unusual points, or it could be an unusual group of points or groupings, or sometimes it's an unusual gap, or other times it's an unusual pattern. So there's any of those things that we could have, and it's something that we'd need to want to talk about. So those are the 4 things. Let's go and have a look at an example of each of them. The best way to get a dot plot is to use NCGraph. So what I'm going to do is I'm going to come in here. I've got NCGraph loaded up here. I'm going to go use the sports science because I think that's a really good data set to use. For what I'm wanting to do, I'm going to look at BMI, which is the body mass index, effectively how fat someone is or how heavy they are for their size. Necessarily how fat they are. And then I'm going to separate it by gender because that one I know is going to work quite nicely. And I'm going to select a dot plot. Alright, so as it comes up here, right, the first thing I do is I look at it and I see, is there a difference in the groups? And it looks like there's one group that's around here and another group that's around here. So it looks like there is a bit of a difference, but as I'll come in here, we'll have a look and we'll see, turn the summaries on and the box plot, and that'll tell us a little bit more about it. A couple of seconds once it loads. Here we go. Okay, so what we can see is that there is a difference. And the things that we want to talk about, first of all, is the center, right? So the mean and the median. What's the difference there? Well, clearly the center of the male sample is higher than the center of the female sample. Now, what we have to be careful here is what we're talking about. We're talking just about the samples. We're not talking about the population yet. We don't talk about the population until we've done our bootstrap. So here's the keys to what we want to talk about. Samples. All right, let's go across here a little bit. Let's fix that up. Samples, not population. Right, the second key I would say is describe what you see first. The first thing I notice is that most of the male data is higher than most of the female data. The next thing that I do then is I give some evidence for it. Right, so the evidence I've got here is that the the median is higher for both of them, and the mean is higher for both. The mean and the median is higher for male than it is for female. Right, now I've talked about the centre. I also want to talk about the shift here, and I'm only going to talk about the shift because there is an obvious difference. If I look here, I've got my lower quartile, the male lower quartile is about 2 higher. The male median is about 2 higher. The male upper quartile is about 2 higher. So overall with those, what it's telling me is that there is a shift. The whole male data basically has been shifted up a little bit. And in fact, even in this case here, the minimum is about 2 higher, and the maximum is about 2 higher. So it really is a case of shifting up. Right? So that's evidence. Then I'd go into a little more detail with the shift. And again, evidence for the shift. Right, so I describe the numbers. Right, the final thing that I'm going to do here is I'm going to talk about what that means and why that might be the case. And in this case here, I'm going to do some research. Okay, so let's assume that I've done this. I'm going to make up the research for the sake of this. All right. So I'm going to describe it. First of all, right, it's going to come out like this. Our male sample has a higher centre than the female sample. We know this because the mean and the median are both higher. The mean and median for the male sample is 23.9 for the mean and 23.6 for the median, whereas the female sample has a mean of 22.0 and 21.8. We can also see that there's been a shift. That it's like the whole male data is shifted up. The lower quartile is roughly 2 higher, the upper quartile is roughly 2 higher, and even the maximum is roughly 2 higher, and the minimum is roughly 2 higher. The distribution is similar as well, so it just really does look like the whole data has just been moved a little bit higher. This may be because males have more testosterone and so therefore grow muscle faster. And this is where I make up my research. Johnson and Shaddy did an investigation in 1974 where they found that increasing the testosterone level caused people to increase their muscle mass faster. As males have more testosterone, therefore we would expect males to have a higher body mass index, particularly male athletes. So that's how we talk about centre. Okay, so the next thing that we're going to talk about is spread. Right, so we start off with the graph that we were looking at before. And what we want to talk about with spread, we have a couple of different variables that we can look at. The two main things we want to look at is the interquartile range, which is the distance from the upper quartile to the lower quartile, and the standard deviation. Right. I don't want to hear any talk about the range. It's really not that relevant. It's the least important out of all of the statistics we can look at. So if we look at this here, right, what we want to do is we want to find our interquartile range. We're going to go upper quartile minus our lower quartile. And we're just going to use, in this case here, we'll work it out quickly. So if we look at the men's data, I'll just get my calculator, right, we have 25.17 minus 22.28, right, which gives us 2.89 as our interquartile range. The interquartile range is actually a really good way of describing how spread out the data is, because it tells us where the middle 50% is, and it's a better method than a lot of the others. Okay, again for the top one, we want to go the upper quartile, which we have here is 23.415 minus our lower quartile 20.235, right, which is 3.18. Right. So if we look at our main evidence for how spread out it is, we've got the interquartile range and we've got the standard deviation. Right. So again, we want to do a similar thing to what we were doing in the last one. We want to first of all say what we see. Right? And they both look roughly as spread out as each other. So that's the first thing we would say is, what do we see? Right. The next thing we want to know after what do we see is evidence. So we want, and this is where we would talk about the IQR and the standard deviation. Now, in this case here, well, which one do we think is more spread out? Well, actually, they're roughly equally spread out. The female data has a higher interquartile range than the male data, but the male data has a higher standard deviation. Now, that doesn't actually happen that often that they're around the opposite way. So in this case here, we'd say really neither of them is more spread out than the other one. We've got a few more points out near at the edge. If we look over here with the male data, which is why it's got the higher standard deviation, but the female, the main box is slightly wider. But it's really, there's no real difference between them. They're roughly the same. So what we hear really is we say there's no real difference between them. Now, that's not always true. There's not always that two samples will be the same. So what we want to do is have a look at somewhere that's not the case. Right? So what I've got here is, I just had a quick look through the data before to find one that it wasn't the case. So FERR, I don't actually know what FERR stands for, but if we look at this one here, remove those over here. This time here we've got a much different data. If we start off by saying what do we see, well, the male one looks like it's more spread out. Right? It's got a higher range, it's got a higher interquartile range, the standard deviation is considerably bigger. Right? So now we've got something we can talk about here, and with this one here we could talk about the difference. And what it means here, in effect, if we look at our male data, we've got our upper quartile of 124, minus our lower quartile of 55, so that's an IQR of 69. Whereas on the female data it's 72 minus 36, so our IQR is 36. So it's almost double the interquartile range of the male. Then if we look at the standard deviation, it's 70% higher. So that's telling us really that the male data is a lot more spread out. All right. Now for that one, we might want to then do some research and find out why is the male data more spread out. And because I don't know what FERR stands for, I've got no idea. But I might do some research into that and find out if there is some reason behind it. The other thing I'd want to know with this is, is it because of some groups? So what I could do is I could colour it by the sport they're playing. Let's see if I can get on that box. Right. So if we look, is there one particular sport that's all up high? Well, not particularly. We can't see any sort of pattern there, but that's the sort of thing that we'd look for. Is there some sort of pattern? And then maybe we'd look at some of the other, is there something to do with the BMI that causes it? If there's a relationship there, we know that the males have the higher BMI, so therefore we'd expect maybe that might be the issue. We'd have a look for a couple of things and see if there's something there. If there isn't anything there, then we just move on. Right? So it's another chance for us to demonstrate some evidence to show what we're doing. And it does look like the higher BMI ends up having a higher FERR, whatever that actually stands for. So it looks like perhaps the reason the males have more in the higher IQ, or the higher, if the higher BMI means that we also tend to have more of them with the higher FERR. Right. So, as well as using the evidence, the interquartile range and standard deviation, we then also want to say what it means. And the big thing that it means is the more spread out it is, the less reliable our data is. Right? If we have data that's all bunched up, then that tells us that it's probably a pretty good representation of the population. Because it's really unlikely from a spread out population that you'll get a bunched up sample. Right? However, if it is all spread out, what it's saying is that probably we can't be so confident about where the median is or the mean is in the population. Because our sample is so spread out, it means that the data is more spread out, which means that we have a wider range, wider confidence interval. So that's one of the things. If you find your data is really spread out, you're less likely to be able to make a call about the difference. Right, let's go and have a look at the next method. Okay, the next one we're going to look at is shape. And what we're wanting to know here really is it normally distributed? Now, one of the cool things that they've got on NZGrapher is they have a histogram function. It's quite a new thing, so we can put on histogram. I think it's new, I didn't see it before. And if we look at the histogram, now we can see pretty clearly what sort of shape the data has. Right, if we take our pen, we can sort of trace it. That doesn't look normal to me. That looks like it's skewed out to the right. And again here, we've got a really steep peak, and then again it drops away sharply and then goes out to the right. Neither of these look particularly normal because the peak is too high, or certainly on the second one, the peak is too high, and then the tail is too long. On the female one, we've got the data skewed, and when you've got the data skewed, it says it's not normally distributed. So the histogram's a really useful thing. We can look at the dot plot and the box plot, and we can see the data. But actually, when you put it into the histogram, it's often a lot more useful. So that's something that you might want to think about, is putting in a histogram, because it's a really useful way. And what you could think about is, if it was normally distributed, you already know what the mean and standard deviation is. You work out, you put a little table. What would we expect it to be, and how close is it to that? That's an option. If you're wanting to go for excellence, that's another sort of excellence option you can do. And the beauty is with the histogram here, it's actually grouped them together. So you could say, well, if we had this mean and this standard deviation, how many would we expect to be between 14 or be under 16? How many would we expect to be between 16 and 18, between 18 and 20? And if you put that together, it will actually tell you what we would expect. And we'll see that for these ones that the numbers are actually quite different. So shape. Again, the same thing that we talk about. First of all, what do we see? All right. The next thing that we want to do is we want to then talk about some evidence. So what do we see? First of all, does it look normal? Does it look not normal? First glance, it looks like maybe it is normal, but when we get in a little bit closer, we see no, it's not. And it's not because it's skewed. We've got this big group out here that, that shouldn't be there if it was normally distributed. Here we've got, our means about here. Oh, sorry. Our means about, let's see if I can get that right, here. And if we look at that distance there, is nowhere near what that distance is. So the skew there tells us that, this isn't right. It's not normally distributed, right? So those are the evidence that we could use. We maybe would put together a table and say, what we would expect and then what we actually find, right? That's all good evidence. The next thing is, what does this mean? And here what we want to talk about is, what could we say is likely in the population? Now, the first thing we want to know about here, and this is really important, is what's the sample size? Because if we know the sample size, that tells us something. In this case here, we've got our sample size of 100 and 102. So it's a medium-sized sample. Now, we would expect some difference from a perfectly normal. Right? Perfectly normal, we would expect, we wouldn't expect to see it looking like the perfect bell curve until we had sort of maybe 500 in our sample size. But with 100, it should be getting close. And this is probably not close enough with a sample size of 100. But that's part of our evidence as well. Can we say here that this is probably normal, that the population is probably normal? Well, no, we can't. Right? So we can't we're not going to make an inference here, but we're going to make a suggestion or an estimate about population. Right, so I'll go through this, how I would answer this one. Right, I start off by saying, it looks like the two graphs are normally distributed at first glance, because they have a peak in the middle, and then the data spread out. However, neither of them are symmetrical. Both of them are skewed to the right, which is some evidence to say that maybe they're not normally distributed. When we look at the histogram, we see the peak seems to be too high, given how spread out the data is. We can also see there's a clear skew with the female data. The group of points that are up between 30 and 34, that group's too high if we had a normally distributed sample with a mean and a standard deviation like they have in the male group. So putting that together, it tells us that probably our populations are not normally distributed. Certainly what we can say is we don't have enough evidence to say that the population is normally distributed, because we would need to have a larger sample size, and the samples would have to look more like a normal distribution bell curve if we were to say that they are probably normal. Okay, the last thing we want to talk about is interesting features. And this can be a number of things. It could be a pattern, or it could be, this one's a little bit less prescribed. You do have to see if there is anything interesting. Is there any groups? Is there anything worth commenting on? And here there is something worth commenting on. And that is that we've got this group out here, and we've got the female here that are quite a lot bigger than the rest of them. In fact, even you could probably extend it out to here. And so we've got these groups here that are quite a lot bigger, and there's enough of them that it's worth commenting on. Right, so to do that, I want to know what these points are. One of the things that I can do, is I can come down and I can do point labels. Now this can be really difficult to see, but it is going to give me something, hopefully, soon. A little bit slow. Right. Now it's going to put numbers in for everything, so that's not really that helpful. But what we can do is we can zoom in a little bit, and we can see this. Right. We've got 15, 17, 20, and 16, 18 are also the highest. So the highest points there, 15, 16, 17, 18, and 20. And then here on the men's side, it's again a little bit harder to read. We certainly have 122, it looks like 114, 121, 124, 116, and 117. So we're going to look at those numbers and see if we can find them. Right, first of all, we look on the women's side. We can get those point labels off for the time being because they're a bit ugly. Right, we knew that it was all like 15 to 20 were our big numbers. All right, and remember we've got the BMI, so it's this column here. All right, so if we look here, we've got 15 is 28. Right, 16 is 26, 17 is 28, 18 is 26, 19 is 25, and 20 is 31. So that's of the women, those are pretty much the highest BMIs, and they're all field athletes. Right. Then if we look down at the men's numbers, it takes a bit of scrolling to get to. If we remember, they were all around about 114, somewhere around there. And again, look what we find. Field athletes. So the ones that had the BMIs over 30. Alright, so we have, what have we got here? We've got one here, which is a field athlete. Field athlete, field athlete. Just under 30, just over 30, over 30. The ones that are over 30, again, are all field athletes. So that's something worth talking about. Right. So our interesting point here for this one is that the larger BMIs are all the field athletes. And it makes me wonder, perhaps if we removed the field athletes, would it look more normally distributed? So that would be something that we could do as going on a little bit further. If we remove the field athletes and just look at people that are in team sports, for example, to remove the field athletes and the sprinters, and just look at team sports and probably include rowers in that because they're probably in a team. Then maybe the numbers will come out differently. Maybe that'll tell us something different. But for the time being, this is what the data is that we have, and if we're looking at all athletes from the Australian Institute of Sport. That includes the field athletes. So when we're talking about our unusual points, we can actually mention where they came from. And that's actually really important information, particularly for later on the analysis. Now, we might want to do a little bit of research into that. We might be able to find that someone that's written about the higher BMI of field athletes. And perhaps we might even find a paper on whether or not they're healthier or unhealthier than normal population. Because the BMI is often associated with a whole lot of issues. And are field athletes more likely to suffer those issues than normal athletes, or than normal people, than normal healthy people? So there's a whole lot of really interesting things with that we could go down. But the big thing that we want to do is we want to talk about what is an unusual thing that we noticed, give some evidence for it, and then a possible explanation, or talk about how we're going to deal with it, preferably using some research. And that's how we get an excellence on this section. We need to have the right graph, and then we have to describe the 4 features using some evidence for each of them and some research as incorporated into it. I hope it's been helpful.